Welcome to Texas State University's Organic Chemistry 2342, Organic Chemistry 2. We're going to continue with Chapter 12, Part 2, Alcohols from Carbonyl Compounds. In the last section, we learned how to reduce down carbonyl compounds to make alcohols. In this one, we're going to talk about oxidizing alcohols to make carbonyl compounds. So we can take primary alcohols and oxidize them to either aldehydes or carboxylic acids by replacing one or two of the hydrogens with our oxygen. So in the case of our primary alcohol, we would just have any generalized alcohol here. We would have a hydrogen, and an OH here. And if we took off one of these hydrogens off of the carbon, we would generate a aldehyde, where we would still have one hydrogen bonded to that carbonyl carbon. Or if we were to continue to oxidize it, we could oxidize off the last hydrogen here and generate our carboxylic acid derivative here, okay? So depending on which oxidizing agent, you can stop at either step when you're oxidizing your primary alcohols. Once we get to a secondary alcohol, things change a little bit because we only have one hydrogen to reduce off of our, carbon here. We can only take our secondary alcohol down to a ketone. We have an R group, and our ketone, okay? Now, in the case of the tertiary alcohols, when we have no hydrogens on the carbon with the OH on here, these are very hard to oxidize, and actually don't oxidize at this carbon here. You have to oxidize one of the other carbons first. So we typically don't react these tertiary alcohols with the system, okay? So now when we react primary alcohols, we can get aldehydes or carboxylic acids, and secondary alcohols, we get ketones. Let's figure out which oxidizing reagents we would use for each, okay? So the primary group of oxidizing agents we'll use are what are called chromium oxidizing agents, and they typically are carried out by using a chromium +6 as the oxidizer, and there's several different derivatives of it. First of all, you can use either chromic oxide, sodium dichromate, or potassium dichromate here. And in the presence of an acid, they became a strong oxidizing agent. They create in situ this chromic acid. You can also use chromic acid itself with no additional acetone, and this is no additional acid required. And you can typically use things in this one in the presence of a ketone for things that aren't water soluble. Notice your alcohol has to be water soluble in the chromic acid and the chromic system. In the chromic acid system, you can use a ketone as your solvent here. The last oxidizing agent I want to talk about is called PCC. PCC is a milder oxidizing agent and is soluble in other materials like dichloromethane. Now, the dichloromethane does not participate in the reaction, but it acts as a solvating agent. So what do these look like? Well, the active ingredient in the chromates are a system right here, where we have basically the chromium in its +6 oxidation state here. And that's basically the active ingredient in all of these materials here. But in the case of our PCC, we have a pyridinium chlorochromate. And so we make a salt with pyridine right here. This is the pyridinium cation because it's protonated with a hydrogen. And then we change slightly the reactivity of the chromine, even though it's still oxidation state of -6, the addition of this chloride reduces down the oxidizing ability of it, and therefore this compound PCC, pyridinium chlorochromate, is not as strong and is more selective, and so we can stop it at different stages in the oxidation. Okay, so let's talk about all of these oxidizing agents can oxidize secondary alcohols to ketones. derivatives. So basically you can take any CH3, CH3OH, with an H here, and oxidize that down with either chromic acid, potassium dichromate, sodium dichromate, or that's a 7 right here. That'll reduce them all the way down to ketones. All secondary alcohols are reduced down, oxidized down to ketones with these chromium oxidizing agents. In fact, if you have a secondary alcohol and you use PCC, it will also oxidize your secondary alcohol down to a ketone. Okay. However, when we go to primary alcohols, we can be very selective on what we use. In the case of primary alcohols, if we want to stop at the aldehyde, we must use PCC for the reaction. So for example, if we had this propanol and we used PCC, pyridinium chlorochromate, we would stop it at the aldehyde right here, okay? However, if we were to use any of the other chromic acid derivatives, so I'm going to use it at the notation of chromium +6 here, any of the other ones, chromic acid or dichromate solutions, that would take it down to the carboxylic acid. Okay, so under those acidic conditions, we can selectively stop at the aldehyde or the carboxylic acid. However, we can also use another reducing agent, another oxidizing agent. In this case, we're going to use potassium permanganate under basic conditions here, if we don't want to use acidic conditions. And what we would do with that is, in the presence of water, we would oxidize all alcohols down to the carboxylic acid. So if we had our primary alcohol again, we could take it and that would look like potassium manganese, permanganate plus base as our first step, and then acidifying at the end, we would regenerate our carboxylic acid to yield that material. This works especially well if your alcohol is not very soluble in acidic water. You can use it as a basic water and pull it in to oxidize it using the potassium permanganate. Okay, in the case of both of these, the stronger oxidizing agents oxidize them down to carboxylic acids. Only PCC will stop the primary alcohol at the aldehyde step. Okay, so how do we know we've done this conversion? Well, when we are reducing these things down to carbonyl, from their carbonyl compounds down to alcohols, we will generate a large signal in the IR, specifically the 3200 to 3600 wave numbers will generate a very broad band right here. And in the case of reducing down a carbonyl, our carbonyl peak will go away and will generate this huge hydrogen bonded OH peak. By NMR, in proton NMR in particular, we will generate a single signal for the hydrogen on the alcohol here, but it tends to be very broad and move around quite a bit. And by the addition of D2O, we'll actually have that hydrogen quickly hydrogen bond off, and that means it will disappear. So you can know which proton is your alcohol proton by adding a little D2O, and it'll disappear in the solution. Now, by the addition of one of these electronegative atoms here, the hydrogens that are on the adjacent carbon are shifted up to the 3 to 4 ppm range right here. And in carbon NMR, having that electronegative atom next to it also increases our shift up to from its normal position at 20 to approximately 50 and 90 ppm in carbon 13 NMR. That completes our chapter 12, part 2.